So let's start the afternoon. Very happy to have Francois Huveneers, who will tell us about absence of normal diffusion in a disordered spin chain.
Thank you very much for your introduction. Thank you for having me here. It's quite a pleasure. So I'm going to speak about disordered spin chain. So it's also quantum model, right? So I think might feel slightly unusual for part of this audience. I hope, nevertheless, you will get something out of the talk. So what is it? So this is, I'm reporting on word that it's not finished basically, right? So it's work with Lydia Giacomin, who was working with me in Paris. Wojciech de Rook, which is in KU Leuven in Belgium. And then Oskar Prosniak, who was student of Wojciech, who is now as a postdoc in Luxembourg. Okay, so the topic is about transport and quantifying transport. So what I have in mind is a 1D system. And it's an extensive system. That means that so you imagine this kind of a chain, right? And this capital L is a thing that will go to infinity. So I'm going to take the length of the system to grow to infinity. And I take a system where there is a conservation law. And, well, you can have many conservation laws, right? But if you take a Hamiltonian system, as I will do, the most obvious conserved quantity is the total energy, right? Because in Hamiltonian systems, the energy is conserved. Right? You could also take electric charge if you prefer working with electric charge. There are all sorts of possible choices, but I think this is the simplest one. I mean, to take just the energy as the conserved quantity. Okay, so the total energy of this system it's an extensive system, meaning that the total energy of this system is just the sum of the local energy. Okay, so each of those particles has its own energy. There is an energy associated to each coupling, and so it's all local. It's a sum that it's extensive. Means if you're going to double the size of your system, you basically double the energy up to small boundary terms, right? So that's what we have in mind. And of course, at a microscopic level, there is a conservation law, which is that everything which flows in must sort of flow out, so that it's always balanced. So the energy, how the energy per site varies, is a difference of the flux coming from the left minus the flux going to the right. Okay, so that's how you write conservation. And well, here's the basic question. So you put this large system between two reservoirs at different temperature, and I will not describe now how you model the reservoirs precisely, but if you are used to classical mechanics, it's usually modeled via Langevin heat bases. For the quantum system, that will not work, so we will have to find something else, but if it helps, you can have that in mind for the moment, it's okay. And so you imagine that here you have some like cold temperature, T0, and here you have some higher temperature, T1, and there will be a flux. So the reservoirs are meant to be like infinite, right? So there will be a persistent flux of energy that will flow from the hot part to the cold part. And exactly like this morning, you expect that a non-equilibrium stationary state will be reached. And it means that you will have the flux here. I mean, here I wrote as if it were depending on time, but it's actually a misprint, right? Because if you are in a non-equilibrium stationary state, it does not longer depend on time, and there is just a constant flux of energy from the hot to the cold, right? And the question of quantifying transport, one way to phrase this question, and at least for those 1D systems, is to say, how does this energy flux depends on the length? So if I increase the length, how does that behave? Okay, that's in a way this is the basic question of my talk, like answering how this current depends on the total length. Okay, and what I will now do, I will provide you with 3 examples that seemingly has not much to do with each other. 3 examples of different behavior with L. Okay, and then I will relate them. So then I will introduce a model where they come all together. Okay, so first model is the most standard. So if you take Ohm's law, so that's even an exercise that maybe you did at secondary school, right? So you have resistances in series. Okay, so like usually Ohm's law is for electric current, well, electric charges, but you can apply it for energy charge as well, and it's just the same, right? And so what tells the Ohm law is that the current in such a system is proportional to the difference of potential, or if you prefer, here in the difference of temperature in the low difference temperature regime, divided by the total resistance, and the total resistance is just the sum of all those resistances, okay? And so the only thing you probably didn't do at secondary school is to take those resistance to be IID, okay? And it will make sense from my point of view to have some disorder to make them random. But so here I took a nice case where I did just some uniform distribution, like I don't remember how I did this numerically, but say between 1 and 2, for example, right? So, and then when you see for a system of size 100 that you get kind of a nice linear shape, right? And it's easy to kind of understand that by the law of large number, this sum of resistances will go like L times the average of the resistance, right? And so here's the answer to my question, like how does J behave as a function of L? Well, like 1 over L, okay? And so that's the thing to remember, that if in the normal case, in the standard case, the current decays like inverse length, okay? So that's the standard thing. Now here is a kind of less standard thing where you take still the same ohmic circuit, but you allow the resistances to have heavy tails, okay? And if you have heavy tails, you cannot, large numbers will not apply the same way, right? Because you cannot compute the average. And in fact, what happens is that this sum of resistances is basically dominated by the highest resistance, right? So if you have such heavy tails, and in that case, it of course depends what distribution you took, but you will still have a power law, but it's not just like 1 over L, it's like 1 over L to some power which is larger than 1, okay? And the physical phenomenology is pretty simple. So you see you have a few, if you look at the potential, where it drops kind of abruptly in a few places. And those places correspond to the atypical, the largest value of this resistance, where the potential drops all of a sudden, right? And I insist here that this is quite 1D phenomenology, right? Because if you were in 2D, it wouldn't work, because then the current could go around the obstacles, right? So it's specific to 1D system. And then the third thing is of a very different kind in a way, which is the thing called localization from the Anderson localization. And I think this sort of fits with the thematic of this workshop, because I think this is fairly well related to the fact that the evolution of the local energy is strongly non-Markovian in this case. So it's strongly self-interacting in some sense, right? So here is an example. So this is harmonic chain, okay? So it's classical dynamics. So on each side you have px, which is the impulsion, and the conjugate variable is qx, right? Which is the where is this oscillator with respect to its equilibrium position. And there is randomness, so those frequencies are all random. It's kind of important for this phenomenology to happen. And then you have harmonic coupling, okay? And it turns out that because it's a harmonic system, Newton's equations, or if you prefer, Hamilton's equations, will be just linear. And it's exactly equivalent to an Anderson model in 1D. Okay, it's equivalent to a quantum one. So this looks like a many-body problem, but it's actually secretly a one-body quantum problem, actually, which just is the result of the fact that equations of motion are linear in this case. Okay, and here the temperature profile is even more sharper than in the previous case. Like you have basically in the middle of the chain, you have it's abruptly drops, right? So we quantified here a little bit numerically how what is the width here, but it's actually pretty narrow. And so, for example, just so you get this profile, and you get a very strong suppression of the current. So the current now is not polynomially suppressed, but it's exponentially suppressed. And this psi that features in this exponential is called localization length of the system. Okay, and because those 1D systems are very much studied in the literature of Anderson localization, I mean, this picture could be made mathematically rigorous, and if you look at this relatively recent paper by Ducates, you will find justification for this profile showing. Okay, good. So those were my 3 introductory examples, and now I want to move to the quantum model where they all come together. Okay, so okay, here it is. So you get once again a 1D system, and it's a bunch of spins that are locally coupled. So and you get it's a purely Hamiltonian evolution, right? So it's a quantum mechanical evolution that I have in mind. That is somewhat important for what I will say. And here it is. So those operators Zx, those are the Pauli matrices acting outside X. So, okay, so you have spins are indexed by small x, right? So x equal 1, 2, 3 up to capital L here. And so Zx is just like Z Pauli matrix plus or minus 1, right? And then you have the usual Ising interaction here, so between nearest neighbor pair. So if you would stop reading the slide here, that's probably an object that is familiar to most of you because it's just Ising model, right? So if you don't want to see those Z as operators, just variables that take value plus or minus 1, right? Except if you want to run quantum mechanics out of it, you better still interpret them as operators, but this is how it is. And so you have this last term, which makes it really quantum in the sense that, so lambda is meant to be a small parameter in the talk, and capital X is the X Pauli matrix. So it's a matrix that it does the quantum flip-flop, right? So there is a spin here, and it was down, and it goes up, or it was up, and it goes down. Okay. So that is what it does. And and it's important for me that there is random magnetic field on each side, because the randomness will play a crucial role. I mean, without randomness, the physics would be completely different. Okay. And here is the phase diagram that people expect, and I will spend a few slides trying to explain what those words mean. So as a function of lambda, what is believed is that, so if lambda is 0, so you just have this classical Hamiltonian. This is called Anderson insulator. It's kind of trivial. I mean, it's not all properties are trivial, but the kind of properties that I want to investigate would then be kind of trivial in that case. And then as lambda increases, we enter in a phase which is called a many-body localized phase. And this is a thing that has started being investigated starting 2005. I mean, Anderson already had kind of this idea in mind, and then there were a few publications in the 80s, but basically around 2004, 2005, they started. So the first big publication was by Pascual and Altschuler in 2006, I guess. And then there has been a bunch of studies on this phenomenology. Okay, so by people like David Hughes, Vadim Oganessian, Dima Banin. I mean, many names that I could cite here, but sort of. So and basically they came to the sort of agreement that the phase diagram should look that way. And then there is a phase transition, and you move from this so-called many-body localized phase to the thermal phase, which resembles more typical. This many-body localized is meant to be atypical, and you go towards something much more typical. Okay, and inside the thermal phase, there is another transition, which is less fundamental than the previous one, between something that is meant to be where the dynamics is subdiffusive, and here is diffusive. Okay, and so what I will try to explain to you is that as you increase lambda, you will encounter the 3 regimes that I was presenting. So here, in this phase, the current is exponentially decreasing as a function of length. And then it becomes like polynomial as a function of the length, but with an exponent larger than 1. And then you eventually get to the normal case where it's like 1 over L. Okay, so the 3 regimes exist in this phase diagram. Maybe it's worth to say that. So this phase transition is not so well understood, right? Yes.
Can you explain how you define capital X with respect to PC?
Yeah, capital X is like this matrix, right? So so X as fluctuations like this Pauli matrix, right? While Z is like this one. But it acts only on the particle at X on your Hilbert space, and it's tensor product with identity. So it's like identity with some power here, then tensor product of this one, and then again identity for the, so it acts only on side X. It acts only non-trivially on side X. That's the way it's defined here. Okay. Yeah, I was saying, so this transition I don't think is very well understood, but it's not, you should not think like it is an equilibrium transition in the sense, if you are used to Ising model, you think, well, okay, that's Ising model, and I know what is a phase transition in the Ising model. I know in particular that in 1D there should be no phase transition, and you're correct about that. So if you look about equilibrium properties, there is nothing interesting. I mean, there might be some interesting things to say, but I mean, if you are looking for phase transition, you will not find it. So if you look at the Gibbs state, there will be nothing special happening if you vary temperature. So what we have to look at something else, right? So it's more like a dynamical phase transition. When if you look at the dynamics, you see that the dynamics is frankly different. Okay, as you cross this one.
What is EDH stand for?
EDH, I'm going to explain in a moment. Okay, so it's a very nice question. What is EDH, right? So yeah, right. So the way I think the way people in this community describes what is good typical thermal material is via this eigenstate thermalization hypothesis, and in its simplest form, what it means is that you take a local observable, like for example the value of the spin at some point, and you sandwich between two eigenstates. I mean between an eigenstate and itself, right? And the value of this local observable within this eigenstate is meant to be in very, very good approximation equal to the thermal value. That means this is the thermal ensemble, the Gibbs ensemble, at a temperature that is provided by the extensive energy of this eigenstate. So you compute so you know the energy associated to this eigenstate. You compute the corresponding temperature, and you evaluate this local observable in the thermal ensemble, and those things should coincide. Okay, these ansatz work very well, right? So I mean, I mean, the systems that violate EDH are pretty much studied because they are exceptional, but for most systems works actually pretty well. This is sort of a relatively abstract way of thinking, but I think we may have a more down-to-earth one, namely that it is a system that obeys usual thermodynamics, in the sense, if you start with you have a large system, when you start on the left with a state at high temperature, and on the right at some lower temperature, or vice versa, and you just wait, and eventually it's gonna equilibrate to a system at intermediate temperature, right? So it is exactly what thermodynamics tells you should happen, namely that you should go to maximal entropy, right? So just the usual statement that if you put all the air particles here of this room into a corner, it eventually will sort of become uniform. Okay, so this is this kind of statement that it's saying. Okay, and the nice thing is then the many-body localized phase can be defined by contrast to this as violating those properties. So a many-body localized system should not obey ETH typically. So that means you take a local observable, and your eigenstates would be such that, so doing the sandwich between two eigenstates would not be the same as evaluating in the Gibbs state, even if you had the right corresponding temperature, so to speak. And just to make better connection with Pierre's part from my talk, I mean, is also total absence of transport. Namely, if initially, you put it was like cold on the left and hot on the right, you wait for as long as you wish, it stays like this. I mean, there might be a little bit of fuzziness here, but like here it may be a little bit like it becomes like intermediate temperature, but sort of as soon as you are away from the center, it stays as it was initially, right? So it is as strange as having something where you put all the air of this room in a corner and it just stays in this corner forever, right? So if you think it that way, it's very atypical material, right? And that's why people get very much interested in this because of so atypical properties. Let me make a few remarks. So first, it holds for closed quantum systems. So if you couple this to phonons or to bars, in a way, you will destroy this. So it's not like a stable thermodynamic phase. No, I mean if you have like symmetry breaking, you know that you can add some stochastic dynamics and you will preserve your phase. That's not the case here, right? So if you put some stochasticity or something like this, you will destroy this thing. I mean, it might perhaps take a long time to destroy it, but you will eventually destroy it. But I think of course, it's unrealistic to believe that something should be isolated from the rest of the world forever. That definitely does not happen. But I think the study of this came from understanding the onset of dissipative effects in solids, right? So you are interested in why is it that a solid by itself should thermalize, and in particular, are there counterexamples? Yeah, there are counterexamples, and so they are interesting to study. So that's probably the way to think about it. So another way to say is that it remembers initial state forever, right? So it keeps memory, keeps very long memory. And a last aspect I want to insist is that this is not an integrable system, right? So if you work with integrable systems, you can have all sorts of strange things. So that like you could violate thermodynamics in an integrable system. Those things are possible, but we have in mind here something a little bit more robust. So it should not be manifestly integrable. So if you perturb the system a little bit in a more or less arbitrary way, that the phenomenology should survive. Okay, so that is that. So it's not fine-tuned. Okay, so this is another important. Yes. So maybe let me try to give a little bit more feeling of what it is. So the best get, especially perhaps for those of you who studied a little bit of Anderson localization, right? So if lambda is equal to 0, then it is in this sense that this model then becomes trivial, because what are the eigenstates are just like classical states plus and minus. Okay, so you just see here plus, here minus, and so on. Okay, you have all eigenstates are like that, and those eigenstates, if you are at this specific point here, this will be obeyed, right? Because, for example, if you take as observable the spin at x, this will be either +1 or -1, which will be different from the average value, which, for example, will be typically 0, right? So it's clear that this would be violated. And if you run dynamics on this system, just nothing happens because there is no possibility for flip-flop, right? So you just stay, if you started like this, you will stay like this, and that's all. So the only thing which is not good about this model is that it's not generic, right? So if I insist of having lambda equals 0, that would be an integrable model, okay? So I want to go a bit beyond. Now, for those of you who studied a bit of Anderson localization, the first intuition you might think is that many body localized eigenstates will be like small perturbation of those, okay? Because if you think of what are Anderson eigenstates for like one body problem, I mean they look like small perturbation of delta of the canonical basis of your system, right? So here you have a very high. I mean, if you have 4 spins, you get those 2 to the 4 states, right? And so you might think that each eigenstate is a little bit like a corner of this cube with a small perturbation. It may be a good first way of thinking about this, but it's not quite correct. So I mean, in very first approximation, why not? I would say, but then I think I have to go a little bit beyond this. And here is the formulation that people have developed. So if I go back to this lambda, so lambda equals 0, just for reminding you, right, is just this Ising model, purely classical Ising model, right? And what you can notice is that you have L integral of motions, namely each of those spins. I mean, they mutually commute, and they commute with the Hamiltonian, so that you have L conserved field. It's an integrable model in that sense. The Hamiltonian is written as a function of them, and they are all local. That means that the spin at x commute with an operator O. So if the operator O acts on another side, it will commute with the spin at x. Okay, and this locality is fairly important. So the sort of theoretical description of many-body localization is that this thing generalizes, except you have to change your z by some more mysterious operators, okay, that we would like to construct. So here is the statement that, at least that is not a theorem so far. We are working on this, but it's not a theorem so far, that if you take sufficiently small lambda, you find a full set of integrals of motions that you might think of not too far from the z operators, but they are not the z operators. So they commute among themselves, they commute with the Hamiltonian. The Hamiltonian is written in terms of them, although it's a more complicated expression than what we had previously. And, which is the most important thing, they are a bit like local. So they cannot be strictly local anymore. But if you commute this tau operator that acts near site I with an operator which is located somewhere else, then the norm of the commutator will decay with the distance, and this psi, you might consider this as localization length of this system, okay? And I would like to insist here that even though the two first properties already look complicated, the real thing here is the third property, because, yeah, so if, just from the fact that, so you see, if your system is finite, so L is finite, so what we have is a very big matrix. Well, you can always, it's a symmetric matrix, so you can always diagonalize a symmetric matrix that we have all learned. And so there is a basis of diagonal operators, and so if you use this basis, you can recast. It's always possible for every symmetric matrix H to find those operators tau that will satisfy those two first properties. So this is just a very abstract general thing will provide you with this, okay? But so it is not very interesting in that sense. What is interesting is that they sort of have this locality property, right? And this is the thing that is not easy to establish. Right, so this picture came from work by Maxim Serbin and collaborators and David Hughes, more or less at the same time. So as I said, the locality is the important thing. And the mathematical proof that we develop is based on trying to rigorously construct those operators that I'm speaking about. Okay, so this is the thing that we are really doing. Okay. Now I think it's time to go to the third part of my phase diagram, right? So far I have sort of quickly said what the thermal phase means to be in the eigenstate thermalization hypothesis. I have tried to explain a little bit what it means to be here. And then I want to say why is it that inside the thermal phase there is again a transition between a subdiffusive and a diffusive phase, which is a sort of less fundamental distinction, but from the point of view of the dynamics, I think is still quite remarkable. So here's the reason, and it's in the same way as the subdiffusion in my previous example was a very 1D phenomenon, it's here again a very 1D phenomenon. But by the way, everything related to many-body localization is believed to only valid in 1D, so it's not quite a big restriction to speak about that. So the reason is that, so that is what physicists call Griffith's effect. So you have here's the material, it's in the thermal phase, so it's like this parameter lambda is large enough, right? But you are close to the transition, and it's a disordered system. So if it's a disordered system, sometimes you have disordered fluctuations. And you can see from your Hamiltonian that having larger disorder is the same as effectively reducing the value of lambda, right? Because you can always rescale the full energy by something, right? So I mean, there are a bit too many free. I mean, not quite, because there is this j here. But let's say if you reduce lambda, or if you increase the range of this hx is kind of a little bit equivalent. And so because of those disordered fluctuations, we end up with pieces of the material that I have shown in blue here, where if they were isolated from the rest of the system, so if they were taken alone, they would be in the other phase. They would be in the MBL phase. So globally the system is in the thermal phase, but if you would isolate this small piece, it would be in the localized phase, okay? And so, I mean, those blue regions are perhaps pretty small, but they are pretty powerful, because if you are in the localized phase, the current is blocked exponentially, okay? So basically you have a competition between two exponentials. So, so what happens is that, so you take a big system of size, capital L, and you look at it as anomalous region. So because it's anomalous, it's like you have to fine-tune a little bit the disorder. Okay, fine-tuning the disorder for a size small l, basically, it's in a typical sample of size capital L would be possible on a stretch of size logarithmic in capital L. So it's pretty small compared to the full length, but the resistance there grows exponentially with this small length, right? So if the current is like inverse resistance, as I had in this original slide, you get exponential of minus log, right? So basically you get a polynomial, and near the transition this parameter will be larger than 1, so that's how you get the subdiffusion, okay? So that's the theoretical explanation for the observation of subdiffusion, and it has been backed by numerics, although I don't think people completely understand, there are numerical observations, there is this theoretical thing, but it doesn't perfectly match, but somehow there is some understanding, okay? Okay, so that's the origin of this. And I want to mention still that I think we have to do mathematics here, because not all people agree with what I said. So although I think most people agree, so here's still a relatively recent paper, 2023, by physicists Dries Seltz and Polkovnikov, who are, they are still kind of famous in this community, right? And they basically are claiming that this all nonsense, and that if you take large enough volume, all this phenomenology disappears, right? So I think it's worth developing trying to develop it mathematically. Okay, this brings me, I think, to the theorem that we proved. So here it is. So we will actually, the part of this phase diagram where we are able to say something is the subdiffusive part, right? So we are able to say that there is a regime of this, if you take lambda small enough, where you will have less than diffusion. It's not that we quantify the subdiffusion, we can say this will be less than diffusion. So here's the system. So you take this chain that I was telling you before, and you put it in contact with two heat reservoirs, so let's say one hot here and one cold there. And coupling quantum systems to reservoir is a little bit harder than classic. So for classical systems, there is a sort of canonical way to go, right? You put Langevin heat bases, and then, yeah, this works very well. There is no obvious equivalent of Langevin heat base for quantum systems. So a sort of easy way to model heat bases in quantum mechanics is a little bit harder. But the thing that you can always do is to know that a heat base is just a very big Hamiltonian system, right? So basically what you have to have in mind here is that you take a very, very big random matrix and another very, very big random matrix, and you look at the energy flux. Okay, so J is the energy flux here in the middle, and the full system is still Hamiltonian, right? So you have a first term that represents this left base, you have another term here that represents this right base, you have a coupling between the left base and the first spin, you have a coupling between the right base and the last spin, and then you have the Hamiltonian of the system, okay? And I'm gonna show you the statement, but let me try to, okay, it's a little bit scary, right? Because there are like 3 subs in a row, but I think it's not that, okay, let me try to explain, right? So this is just a consequence of the difficulty of modeling bases in quantum mechanics. So we want to look at the steady, ideally we would like to look at a steady state current. We don't know whether there will be a steady state current in the system. So we take time average current, okay? So if there is a steady state current, taking long time average or steady state should be the same thing, right? Now what is important to do is to first send the size of the base to infinity before sending time to infinity. Why? Because if you would do it the wrong way around, so if those bases would be finite, then they can only transmit a certain amount of energy from left to right, and then it's finished, right? So, and if it's finished, then if you do then your long time integral, then you get 0. That's not, we would get, the theorem would still be valid, but totally uninteresting. It's important to first say, well, let's send the size of those bars to infinity. We measure the current at some time t after having sent the size of those bars to infinity, and then we take the large time limit, right? Because in this way, I think we capture the physics that we really want to capture. Okay, so that's why what we do is we take the supremum over all initial density matrices, then the supremum over all possible. You can take whatever you wish for those bases. So whatever matrix. Of course, the idea is to take some density matrix with some temperature on the left, another density matrix with another temperature on the right, something like this. That's the most physical choice, but you can take whatever you want. And once this is, those supremums are taken, we take the long time limit of the current, okay? And so if there is a non-equilibrium stationary state that sets in this system, this will be covered. So this would be a particular case of the non-equilibrium stationary state. The theorem is as follows, that basically, so if you take expectation over disorder, well, this current here as a function of the length of the system decays faster than 1 over L. Okay, so it is what I announced before, that it's a subdiffusive regime. Right? You could be more quantitative. So if you don't want, if you remove the expectation here, you could, for example, with high probability, you know according to what power it decays, like as a function of the parameter lambda of the model. Okay, so you could be more precise if you wish, but I think this is the main message. Yeah. So yeah. Sorry.
So you said you're in the subdiffusive phase and not in the
yeah. It's a good question, right? So I understand your puzzlement. So let me try to go back to this phase diagram. So we prove subdiffusion in the sense no more than diffusion, but we prove it here, right? So that means that we prove it in a place of this phase diagram where probably one should be able to say much more. Okay, I'm not sure we are able to say much more. Probably we should be able to say much more, but that's so far what we can do. And actually, it might sound a little bit not that much, but it already goes against the message of some numerics. Like there are people who are claiming, no, this subdiffusive phase just does not exist. Well, it does exist, right? Maybe not in the regime that they have investigated, but it does. Yeah, so that's a fair comment. Another comment. So I insist for saying that those many-model localized systems should not be fine-tuned. And so here I took a kind of specific perturbation, and you might worry that it's actually fine-tuned, but the theorem is more general. So I mean, you can replace this term by something a little bit more sort of in some class of operators. It will be fine, right? So I think this robustness aspect is we do cover. Okay. Yeah. So that's yeah. Last funny thing is that so in the early days of many-model delocalization, initially this transport property was taken as a characterization of many-model delocalization. So in those early works by Gorny, Emilin, Polyakov in 2005, and then by Bascualano and Schuller, they said, well, what is a many-model delocalized system? What is a system where this is valid? It has been realized that it's not a good characterization. It's too weak for being a good characterization, but somehow it means like nearly 20 years after they postulated this, it seems we have proven that. Okay, so I think I have still like something like 15 minutes or so. So I'd like to explain a little bit the strategy of proof of this theory. Yeah. So we have been following a mathematical approach that has been created by John Imbrie. So he wrote 2 very, very nice papers in 2016. So it's a mathematician, right? But the papers are not completely mathematical, right? So all sort of issues with them, but it's a very interesting strategy. So the goal. So what we are doing, we are diagonalizing a matrix, okay? But as I said, as such, that is easy, but we want to have some property of this diagonalization. And the property that we are after is that, so this orthogonal matrix U should preserve the locality of operators, okay? That is quite remarkable. I mean, if you think about most systems, you perhaps know integrable systems, like a typical example of change of basis is the Fourier change of basis, right? So, and Fourier change of basis is a typical example that does not preserve locality, because if you are local in X space, you are not local in Fourier space, vice versa, right? So one way to phrase here the localization is that the change of basis that diagonalizes your Hamiltonian does preserve locality. So it's very, very different from the Fourier change of variable. Well, I mean, besides the fact that it's here a many-body system. right? So the idea is that if O is a local operator, like spin at some point x, you rotate it in these bases that diagonalize the Hamiltonian. It is not going to stay exactly local. That is, you cannot expect that. But it will be written as a sequence of operators that are supported on some intervals. And if you take those intervals longer and longer, the norm of those operators will decay. Okay, so that's what is usually called like quasi-local operators. And the idea is to do that not in one go, but in many steps. So to set up an iterative procedure. So like you first do some transformation that will make it closer to diagonal. You do this transformation, and then you get a new Hamiltonian, and you start again, and you redo a new transformation to make it even closer to diagonal, and you keep going like this. Okay, so I think it's sometimes I mean, there are some like numerical methods that work that way actually. So like I think it's called Jacobi method. It comes in many names. So in the literature on this business, it's usually called Scriffle-Wolf. Sometimes called Jacobi method. Is also extremely similar to what is KM theory in classical mechanics. It's kind of an example of a KM theorem that holds at infinite volume at positive temperature. So it's easier than KM theorem in the sense that we work with matrices. Okay, so which makes several aspects simpler, but we want to do it in an extended system, which creates new difficulty that are absent if you are looking only at a few body problem. Okay, so let's try to do one. Okay, let's try to do how it looks like. So what you do is, this first one, you try to diagonalize this Hamiltonian. And so I assume that my Hamiltonian is like, so E is like this Ising model, which is, it's already diagonal, right? Because it's just Z operators. And you have this perturbation, which is just this flip-flop term that acts locally. And lambda is meant to be small. And you try to have your change of variable like exponential of lambda A with A as anti-symmetric matrix, which is guarantee you get an orthogonal transformation. And what you do is you just, okay, you can rewrite it this way, and you just Taylor expand your exponential, and you say, well, let's try to diagonalize in the sense that we will remove terms that are perturbation that are order lambda. We'll try to design this A matrix so that the perturbation of order lambda is removed. Okay, you only are left with a perturbation that is lambda square. So if you manage to do that, you have improved your situation, right? You had a Hamiltonian which was diagonal plus perturbation of order lambda, and you then will have a new Hamiltonian which is diagonal plus something of order lambda square, which is smaller. So you're closer to diagonal, okay? And well, just some algebra you can do that. Okay, you can find this A, and here's the answer. So if you V, your perturbation is like those sum of the flip-flop terms. The A is again sum of the flip-flop terms, but, and here's the big danger, you pick a denominator, which is an energy difference. So it's an energy difference between initial and final state, which I wrote explicitly here, but it doesn't matter very much. And those are the thing that will cause all the trouble, because sometimes so we call it a resonance. So if the energy difference is nearly zero, well, manifestly you are going to have a problem here, right? So because you cannot divide by zero. So if it's non-zero, things are going to be fine, because then what you will have is that you will have e to a small lambda times A, and A will be a sum of local terms, and it can be checked that if it's of that form, then it does preserve locality as we want it. Okay, so if you're ready to ignore, if you're keen to ignore those denominators, then we are actually in business. Okay. So, as I said, however, the problem are that sometimes you get those resonances, so sometimes it can get very small. So the main technical difficulty, if you wish, is to control those things, so that you have to show that this does not happen too often. And it's a bit harder than for the Anderson localization, because in Anderson localization, so you have L sides, and your Hilbert space is just dimension L, so you have you have one fresh disorder for each variable, right? But here we have a much higher Hilbert space, which is 2 to the L, right? But still same number of random variables here.
So in this energy difference, this is actually a matrix, right?
It's a matrix, yeah.
And but these are all on different sites. So how does it cancel?
Well,
Does it mean
it's
an
kind of
arbitrary
an easy matrix in the sense that there are only Z operators, right? So you can view it as a function. So if you think that you are in the classical basis where you prescribe a plus or minus for each site, then in this basis you can easily compute this. This becomes like a number, right? Because you don't have the things that are in those denominators only involve Z operators. So if in this basis they act like functions. So you can view them as numbers.
Okay.
And if it's not obvious that it will stay like this if I iterate the scheme, but it is. So the denominators will always be just function of those Z's, so just diagonal operators. So because we have in mind that when we say we diagonalize in the basis of those Z's. So we basically view those as numbers. Basically, if you would fix the initial state, it would just a number. Okay, yeah. So in that sense, this inverse here is not problematic.
So it just depends on the value of H then.
What?
So
Right. It's the value of the field here. So the fact that it's random is good and it's bad. And it's kind of crucial to have randomness because it's thanks to this randomness that you can sort of with sufficiently high probability make sure that this thing is not going to be zero. But the sort of you cannot avoid that sometimes it will, right? So and maybe in first order like here you can, for example, choose uj or something in such a way that it does not happen, but you will get stuck at some point with this strategy. So if you when you move to higher orders, you get much more terms, and there is no easy way, I guess, to guarantee that you never reach a resonance. So basically, at some point you have to face the problem. Okay, and so I think that the control of those things is I think one of the reasons why there is so far no proof of real MBL. I mean, we managed to get, I think, no proof of this subdiffusive transport, but the proof of real many delocalization is not there yet, and one main reason is that those things are hard to control. And John Imbries, in his nice work, had to introduce, he had to introduce an hypothesis on the model that he could not check. So like he said that, well, I suppose that the spectrum has this and this property, but I don't know. I mean, it was very plausible it has, but that's not good to prove. But for us, life will be a little bit easier, and the reason is that, as I introduced, we only need the real localization on some small stretches. So what we will actually do in the proof is try to search for the best stretch where all those resonances do not appear. Okay, so and we prove that what we are proving seems weak. So we prove that on a system of size L, small l, which will be this log of capital L, we have the real MBL, but with very small probability, actually exponentially small probability in the coupling constant lambda. Okay. Yes. So not that much time left. Let me try to still perhaps sketch a little bit the proof. So, okay, you do this first step, okay, and you are in a place where you get no resonances. So, and then you have to continue, right? You have to do infinitely many steps. And so the first cartoon you have is that now, after having done one transformation, you get a diagonal Hamiltonian. Actually, the energy needs to be a bit renormalized, but let's skip this. And you have a perturbation, which instead of being for the lambda, is now for the lambda square, right? Because we gain something, okay? So basically, you had the initial V was like the flip-flop at point X. We created the A by bringing a denominator. And then the new perturbation looks like, in first order, kind of this commutator. And so basically you get a product of V and an A, right? So you have the V here, which is this X, and then you get this A, which is there. And because it's a commutator, they have to be nearby. So the X and the Y have to be nearby point, otherwise they would commute. Okay, if they would commute, you just vanish. So that is the thing that keeps locality in the system. And then you create a new A, and when you create a new A, well, you insert a new denominator here, and it spans more sides. Okay, so the energy is a bit more complicated. And then, well, you proceed, right? So, and eventually at scale n, you're going to have a coupling constant that, if things would go perfectly well, like in the Newton-Raphson method, it's like a quadratic scheme, actually, right? So you would get like a perturbation of order lambda to the 2 to the n, which is not exactly what happens because it's a bit more subtle, but basically that is what you expect. Okay, and you can draw diagrams for that. I mean, I'm going to spare you this, right? But basically, every arch here represents a denominator. So it's a way to figure out how many denominators you get. Okay. The thing is, you have to define some kind of resonance threshold. So that means this denominator cannot be smaller than something. Okay. Otherwise, you have to reject. You have to say no. This sample is not good as there is a resonance. Okay. And you don't have much choice for what the resonance threshold is. Is that if you as you continue doing this perturbation, you get higher and higher terms which involve more and more bodies, right? And eventually, if you get an R-body term, the resonance threshold should be some epsilon to the power R. You cannot take it much smaller, this threshold, because it would be good to take it smaller, because then you would have it with high probability, but you would kill your exponential decay. Or you could try to get it larger, but if you get it larger, it will be better for your convergence of your series, but then you have it with too small probability, okay, to have the result with 1. So basically there is only one way to go, is to have something that decays exponentially with the number of terms here, okay. And the thing that was already observed by Embry is that if you really do the scheme the way I propose, namely like inductive, namely like you first do a first rotation and you start afresh with a new Hamiltonian and you start again and again. You look at the naive convergence of this series and you see that there is an unfortunate n here. So you have the coupling constant becomes lambda to the power 2n, but there are a little bit too much of denominators, and instead of having epsilon to the 2n, you have epsilon to the n to n, and that's never going to work. So that means this expansion cannot be controlled in a purely perturbative. That's the thing Embry noticed already, right? So this thing cannot be controlled in a purely perturbative manner, because if you do it purely inductively, it's not going to work. So the key to get rid of that is to realize that being purely inductive is fairly pessimistic, because if you are purely inductive, that means that you always assume that you were in the worst case. Okay, well, that is no reason to believe that you are always in the worst case. So basically, what you have to do at some point is to say, well, some diagrams, we will re-estimate them probabilistically, and then you can improve on this. But so at the end of the day, the philosophy is that of the renormalization group, but we don't follow the philosophy to the end, because we need to keep information on what was at the very first scale, actually, of the scale. Okay, so this was a technical thing, but I think there's no time left. So let me just come to conclusion. So I think we are at the exciting moment where we develop still the mathematical theory of medieval delocalization, which is still from the physics point of view, is still like 20 years old, but there are not much mathematical works on this. So the theorem that we now get is an absence of diffusion. It's heavily inspired by this wonderful work by John Embry, and I think it already kind of rules out some things that were claimed based on numerics. So thank you for your attention.
Thanks very much. Are there questions? So one very naive question is, because it's a somewhat probabilistic object sometimes, that sometimes these models can be recast in terms of sort of space-time loop-type models, quantum systems, but I don't know what that means with the baths. Is there such a picture here?
Yeah, no, with baths I don't know, but I mean, most of what we do is without baths, right? Because basically what we're doing is we consider an isolated system. I mean, we look at first at the isolated system. We try to establish something on the isolated system. And then basically the idea is to say, well, once you recouple this with the baths, then the fact that we know that the transmission of the conserved quantity is so weak, so bad in its small stretch, basically whatever you put for the bars will be fine. I mean, you will sort of, because it's 1D, well, it will act as a bottleneck. So if you have an idea as a nice representation in terms of loops, maybe it's a good idea, yes. We didn't think that way. But, yeah.
Are there any other questions?
Yeah, another naive question. So how can you see that when lambda increases, you sort of create bigger like trap bottleneck zones in the system?
So when lambda increases, I mean, the naive thing you can say is like it becomes harder to control this expansion. So expect that it might diverge, but there's not proof, right? I mean, so the only thing at a mathematical level, right? The only thing you can say is that you don't have any argument anymore to think that the expansion is convergent, and numerics and physical arguments suggest that it's actually divergent. I mean, it's never completely divergent, but the sort of which is important is that the convergence does not depend on the length, and the convergence would start becoming dependent on the length, and then you lose all the properties, right? But I don't think there is any really very good argument to say that. I mean, at the mathematical level, I think there is nothing to say that it has to break.
Any other questions?
Yeah.
This is pretty basic, I guess. So if you have, you had your Hamiltonian originally for the chain, and then you coupled it to these bars, and then you're looking at this quantity J, this sort of flux through, and you're wanting to look at localization in terms of effectively this quantity here. How does this not directly relate just to the eigenstates of the original Hamiltonian? Like if you have localization there, then you have localization here, or vice versa?
So I think, you see, so once you couple the system to the bars, right? If your bars is finite, then eventually, I think if you look at the eigenstate of this chain coupled with the bases, then it's a bit like considering the wrong limit, I mean wrong. I mean not what we want. So in the sense like you will look at the finite system and look at this long time asymptotics. While I think those eigenstates. No, I think those eigenstates could be delocalized.
Eigenstates of what? Of the whole?
Of this full system. I mean, even here, even without coupling to the bars, right? So we have on some stretches we can establish some localization, but once you recouple it to the full system, it can well be where you have some resonances. It can well be that those eigenstates eventually are delocalized.
Because if you have localization just on the chain, then that doesn't preclude you from, after you couple to, because I mean, in order for you effectively couple the eigenstates of both the baths to the chain through these like small terms to the boundaries. Do you not just see that, well, nothing overlaps really, so it just can't propagate through?
Well, I mean, unless the bars are pretty small compared to the full chain, I mean, if the bars are relatively small compared to the full length of the chain, then it could be that indeed it's just something locally happening. But if your bars are much bigger than the length of the chain, then I guess most likely the eigenstates will be actually completely delocalized. Would be my guess. We can discuss further.
Okay, I think it's a good time to thank Francois again and have a tea break.
Thank you.